Commercial Applications for Autonomous Vehicles by Alex Creech, Alex Veeder, Brandon Russell, and Daniela Lorota Bonilla. In this video, we will be discussing the overview, a brief history, relevant IT components, uses and implications, relevant costs, benefits, and risks, and future trends of autonomous commercial vehicles. Gartner, a leading technology and research firm, defines an autonomous vehicle as one that can drive itself from a starting point to a predetermined destination in autopilot mode using various in-vehicle technologies and sensors, including adaptive cruise control, active steering, anti-lock braking systems, GPS navigation technology, lasers, and radar. Much as the first smartphones were revolutionary for putting our calculator, email, texting, games, and phone calls all onto one device, the same can be said of autonomous vehicles. Self-driving cars combine GPS, LiDAR, cameras, radar, sensors, and a computer, and combines them all into a roadworthy vehicle. And we will discuss all of these IT components later in the presentation. The Society of Automotive Engineers have identified 6 levels of vehicle autonomy. The first level is level 0, no automation. The driver is performing all of the driving tasks. Level 1 is driver assistance. The vehicle is controlled by the driver, but there are some driving assist features. Level 2 is partial automation. The vehicle has combined automated functions like acceleration and steering, but the driver must remain engaged with most driving tasks. Level 3 is conditional automation. The driver is a necessity, but is not required to monitor the environment. The driver must be ready to take control of the vehicle at all times with notice. Level 4 is high automation. The vehicle is capable of performing all of the driving functions, but there still needs to be a driver that has either options to be there or possibility of not being there. Level 5 is full automation. The vehicle is capable of performing all driving functions under all conditions. The driver may have the option to control the vehicle.
And now into the history of autonomous vehicles. In 1926, the first radio-controlled convoy car, as they called it, the Limericken Wonder, was created by Houdina Radio Control in New York City. The car had antennae scattered on it and received transmissions from the vehicle in front of it as, quote-unquote, the lead car. These transmissions were sent to circuit breakers within the second vehicle that directed the electric motors to perform certain tasks. In 1939, General Motors sponsored Mr. Getty's exhibit, The Futurama, at the World's Fair. He built an electric vehicle that followed radio circuits. In 1953, RCA Labs built a miniature vehicle. They buried electrical wires in the road, and the technology they installed allowed the vehicle to follow these wires. In 1958, Mr. Ress, a traffic engineer from Nebraska, added to RCA's project and buried the circuits in 121 meters of road in Lincoln, Nebraska. The track also had lights that would send impulses that would guide the car and also send stats back to their trackers. In the early 60s, technology began to progress, and GM partnered on Ross's project. One of the advancements was an electronic guide system. This allowed it to drive on the highway without human intervention. In the 1960s, UK tested magnetic cables in the road to propel a vehicle. They found that this testing was way more efficient than human-controlled vehicles. In 1966, Ohio State University's Communications and Control Systems Laboratory launched a project to develop driverless cars. The vehicles were activated by electronic devices in the road. In 1980, Mercedes-Benz created a robotic van. This van eventually led to the uses of LiDAR, radar, GPS, and computer vision in vehicles. These technologies that we use today in our autonomous vehicles. Examples of these include adaptive cruise control, steer assist, lane parking, and early braking. Between 1987 and 1995, many projects took place, one of these being Eureka's Prometheus project. Many organizations came together to perform this project. It led to the first use of LiDAR computer vision. One of these organizations was HRL Labs. They were able to perform the first off-road test with an autonomous vehicle. Another project during that same time period was the Autonomous Land Vehicle Project. Many organizations came together on this project as well, and over $1 billion was spent between this project, the Prometheus project, as well as many others. In 1991, the U.S. passes the ISCEA Transportation Authorization Bill. This bill directed the U.S. DOT to create an electric autonomous. GM and UC Berkeley were its main contributors. In 1997, San Diego was chosen as a location. However, this project lacked funding back then and fell through. We move on to 1991 again. Mercedes-Benz again creates a vehicle that's able to travel 1,000 kilometers on a 3-lane highway in dense traffic. It did, however, have a decent amount of human intervention. In 1995, Mercedes-Benz drives the vehicle to Copenhagen, Denmark. This vehicle used jolting computer vision microprocessors that were designed for parallel processing to react in real time. This vehicle was autonomously driving 95% of the time. Also in 1995, Carnegie Mellon University's NavLab project took a car 5,000 kilometers across the country, receiving 98.2% autonomous. However, this vehicle was semi-autonomous in nature, and neural network controlled the steering and the brakes throttle were controlled by a human. Next, in 1996, Alberto Broggi from the University of Parma launched the Argo project. This vehicle was created to follow painted lines in the road. It operated without human interaction for 94% of its trip. In the early 2000s, autonomous public transportation became active. Park Shuttle became active in the Netherlands as well as others around the world. In 2010, Segway and GM created a 2-seat electric car that could be driven autonomously. This vehicle was the beginning of higher level tech being used, for example, vehicle connectivity and motion control algorithms. On October 28th, VIS Labs International in 2010 went 13,000 kilometers with 4 autonomous vehicles. The journey went through several countries from Italy to China and showed that these vehicles can travel over long distances. In 2013, VIS Labs advanced autonomous car, the Brave, was created. It was able to navigate down narrow rural roads through crosswalks and operate safely at traffic lights. In 2013, the Nissan Leaf was the first modern roadworthy vehicle with autonomous tech. It only had a test drive at first, but Nissan was hoping to have autonomous vehicles by 2020. In 2014, Navia, created by Induct Technologies in France, used LiDAR and optical cameras, and no road modifications were needed for it to perform autonomously. In 2014, Google announced that they were creating an R&D department for autonomous vehicles. They announced that they have a goal to create 100 driverless prototypes. Between 2014 and today, there's been a lot of progress in regards to the technologies previously mentioned. Companies like GM, Ford, Tesla, Zoox, and Embark all are working to have breakthroughs in this field and be the first movers to successfully create autonomous vehicles.
You're probably wondering, how does a computer, or in this case, autonomous vehicle, come close to human intelligence when doing something so complex? To answer that, we need to understand the 5 main components that make up autonomous vehicles. The first 3 are part of hardware. Number 1 is a sensor fusion. Being able to understand the environment in a detailed manner is fundamental for autonomous vehicles. Because there are a bunch of sensors equipped on an AV, we can take all the necessary data and fuse them to provide a richer diagram for our vehicle, hence the name sensor fusion. Actuators are the components of a machine responsible for controlling and moving the system. Actuators are like muscles of your body responding to electrochemical signals from your brain so that you move such parts as your arm or your leg. V2X technology, V2V, and V2I technology. V2V and V2I components enable the autonomous vehicles to talk and receive information from other machine agents in the environment, such as transmitted information from a city light that it has turned green or warning from an oncoming car. Next is software. Computer vision. In computer vision for AVs, the goal is to be able to identify objects near the vehicle. We do that using an image classification network called convolutional neural networks. The next and last is localization. In autonomous vehicles, we want to be able to figure out where our car is in the real world so that we can make better decisions on how we get from point A to point B. This is where things get complicated and require complex math algorithms to create something similar to GPS. The planning system refers to the ability of an autonomous vehicle to make certain decisions to achieve some higher order goals. This is how the autonomous vehicle knows what to do in a situation, whether to stop, go, slow down, etc. The planning system works by combining the process information about the environment, i.e. from the sensors in the V2X components, with established policies and knowledge about how to navigate in the environment. The control system pertains to the process of converting the intentions and goals derived from the planning system into actions. Here, the control system tells the hardware, the actuators, the necessary inputs that will lead to the desired motions. Autonomous technology is ushering in a new era of commercial transportation. One of those eras is in public transport. Being reliable, autonomous technology to public transportation could thus provide immediate benefits to American communities concerned about personal vehicles' environmental impacts. The next would be freight and locomotive. Locomotion is bringing its self-driving trucks off the test track and onto the highway this spring. The company recently announced a partnership with transportation logistics company Wilson Logistics to move cargo on autonomous trucks more than 400 miles between Oregon and Idaho. And then the next use would be driving safety. A major goal for driverless cars include a significant health and safety benefit. They are expected to reduce traffic accidents and fatalities. According to the National Highway Traffic Safety Administration, 35,092 people were killed in 2015 in automobile accidents on U.S. roads. Some of the implications of autonomous vehicles could include unemployment. If cars, trucks, and buses start driving themselves, people who earn their living from these vehicles will suddenly find themselves out of a job. There's the possibility of hacking. Recently, security experts looking to exploit flaws in modern automobiles successfully hacked and were able to take control of a Tesla Model S and a Jeep Cherokee. A driverless car would be entirely controlled by computer hardware and software, and a malicious attacker could find and exploit security holes in any number of complex systems to take over a car or even cause it to crash purposefully. The auto industry is another implication. It could hurt the auto industry and cause potential consequences of a world with driverless cars is that people will rely more on calling a driverless car from a shared fleet similar to calling an Uber. Causing a decline in the private ownership of vehicles could lessen the economy. The development of autonomous commercial vehicles is not for the faint of heart. The costs implicated with creating the technologies and the vehicles to put them in is extremely high. However, there are even higher cost-saving benefits to the autonomous world of commercial vehicles. In Australia, the most truck-dependent country on Earth, Caterpillar and its reseller WestRack have converted 22 of CAT's 2,600 horsepower, 430-ton 793F mining trucks into autonomous trucks at mining conglomerates. And it's been reported that each truck just at the Yandy mine, as it is known, saves 500 Commercial autonomous vehicles will likely roll out in 4 waves. The first wave, which was been tested from Arizona, is where they are platooning. So you have a driver in each truck, and what these trucks are doing is following each other on highways. So you have 2 driver platoons, 2 trucks on interstate highway. Drivers drive individually on non-interstate highways. The second phase is platooning on the interstate highway between dedicated truck stops with 2 trucks, with a single driver in the lead vehicle. So the driver would be driving himself in the very front, and then the autonomous commercial vehicles would be following behind him. The third, constrained autonomy, is where the autonomous trucks ride on interstate highways without drivers, and there's platooning, so 2 or more trucks when possible. The drivers drop off the trucks at dedicated truck stops. So the trucks themselves would drive on the interstates by themselves, arrive at the truck stop, and then the driver would take it over for any other roads. Autonomous trucks in the fourth phase, autonomous trucks drive individually on all highways and in platoons of 2 or more trucks. The driver involvement is eliminated throughout the entire journey, so these trucks are now able to drive on city roads, back roads, and those sorts of roads. What this implies, though, is the total cost of ownership and savings. As you can see, we start out at 100% total cost of ownership, and for each phase it drops all the way down to the 4th wave of full autonomy, and the total cost savings is 45%, meaning that the cost of owning these vehicle fleets is almost cut in half. Statistics show that the labor alone account for 30 to 75% of the trucking costs. Human drivers are also restricted by law to no more than 11 hours per day, which is why you see a lot of long-haul drivers, there's 2 people per truck. Autonomous trucks would allow the truck to remain on the road essentially 24/7. Other statistics also point to cost savings. For example, Derek Kaufman, managing partner of Schwartz Advisors, highlights the potential insurance cost savings to both owner-operators and fleets, with no bodily injury for the drivers would need to be occurred. Scott Grinnerth, the Director of Regulatory Affairs for the Owner-Operator Independent Drivers Association, representing over 350,000 owner-operators in the U.S., says that I don't see computing being able to account for every situation a trucker might experience. Another downside is the presumed shift in the labor force, with hundreds of thousands of traditional long-haul trucking jobs becoming redundant. The main issues when it comes to risks, just like Scott Grinnerth stated in the Safety on the Road to Other Civilian Drivers, what would the truck do in certain situations? Who is at fault in an accident? And national job security. Well, if there happens to be an accident, there would be no driver to explain what happened except for the civilian driver, leaving the trucking companies always at fault. And how many scenarios are needed to create a safe and efficient autonomous truck? How many times do they have to rerun these situations to perfect an algorithm? The trucking industry is the main job supplier in 28 states across America. Autonomous vehicles would eliminate a lot of those jobs. Well, these issues can all be summed up and sort of explained anyways. These autonomous trucks would be able to react faster and more efficiently than a human's reactions, recording all the movements just like a black box in an airplane. So the insurance companies would be able to review the black boxes and find out who truly was at fault. This would create for a safer environment for both autonomous and civilian travelers. The job security is a big issue, but realistically there's a shortage of truck drivers in America as it is. Their turnover is not being replaced by younger generations of truck drivers. So in turn, most of the current drivers would just need further education in order to complete the autonomous vehicles or become logistical operators. The job security would remain relatively the same in terms of numbers. However, their salaries would likely increase. To expand on the benefits of autonomous vehicles, using geolocation of trucks and seeing when trucks are running empty could allow trucks to be dispatched to places where their services are needed. However, this would require the drivers to be on the roads longer. If you have autonomous trucks, this would allow these companies to utilize all the capacity of their trucks around the clock. Take, for instance, right now the COVID-19 crisis. Using geolocations, a lot of these companies now are eliminating certain routes that are COVID-19 case heavy. Having autonomous trucks would allow the use of geolocation to keep drivers safe, as well as allow these companies to keep their drivers away from severe case cities, allowing them to utilize the autonomous trucks for long distance and keeping the drivers local for now. Some effects and quantities and values. Saved driver costs for long distance. 15% of long distance transport by AV in 2025 is driver free, with 50% being in 2050. Save driver costs for other transport by truck. 10% of distribution and 20% of construction vehicles that are AV are driver free in 2025, with 50% in 2040. Save fuel and environmental costs due to convoy or platooning. Convoy, 10% of long distance in 2025 and 50% in 2040, with a 10% saved fuel cost. Increased traffic safety. 10% fewer accidents in 2025 and 30% in 2040 compared with today. Net benefit new traffic and added posts for difference between prime and MC. Price elasticity of demand for long distance is 0.8, other transport 0.5. Price 20% over marginal cost. And the adjustment post transferred traffic from train, 5% of new long distance transported transferred from train, which means that they can get these locomotives as well to be autonomous. Technology companies continue to pour big money into research and development in the race to produce the first commercial autonomous vehicle. As yet, there is no commercially viable integrated solution for trucks. Leaders in this niche include Waymo and Uber in the US, Bosch in Europe, and Baidu and TuSimple in China. The use of autonomous commercial vehicles would create more jobs and profit pools than it's destroying. Take a look at today's chart and in 2030. Looking at this chart, we can see it would create autonomous vehicle, commercial vehicle sales, fleet management services, pay-per-use commercial vehicle sales, autonomous vehicle fleet operation management, last mile delivery systems, autonomous vehicle software companies would explode, and new automation companies creating new NEV powertrains. Combined with new technology and components, these services, which accounted for just $1 billion in profits in 2018, will explode to account for nearly $10 billion by 2030, creating profit pools almost 4 times the size of the internal combustion engine shortfall. Subject to progress on the technical, infrastructure, and regulatory challenges, up to 15% of all new vehicles sold in 2030 could be fully autonomous. Regulatory challenges overcome in key markets, safe and reliable technical solutions fully developed, consumers enthusiastically and willing to pay would all be high disruption scenarios. As you can see, commercial introduction of full autonomy by new tech players and premium OEMs around 2023, manufacturing capacity for tech players ramps up gradually around 2025. Mass market leaders introduce full autonomy by 2030. Ramp up as AV availability spreads across popular consumer models. That's where the high disruption scenarios for conditional or better autonomy L3 to L4 would put us at close to 80 to 90% full autonomy by 2040. In a low disruption scenario for conditional or better autonomy L3 or L4, which is full autonomous, would be technical and regulatory barriers delay commercial scale introduction of autonomous vehicles. Or you'd have a slow consumer uptake driven by low perceived value proposition or negative publicity following critical incidents. It now takes the average U.S. worker 25 minutes to travel to work, 45 if you live in Jacksonville, according to the U.S. Census Bureau. Autonomous vehicles are expected to free up time for passengers to focus other tasks, including work, socializing, viewing entertainment, etc. Bosch has created a show card to display the company's digital living environment inside autonomous vehicles. It features large surface monitors with the ability to have video conferences, display real-time traffic and weather information, email accessibility, as well as entertainment options. As autonomous vehicles improve and their computing power in these vehicles is increasing, automobiles become more like computers with wheels. They are increasingly becoming connected and with artificial intelligence capabilities will predictively identify maintenance needs. By combining data from advanced Internet of Things sensors, maintenance logs, and other external sources, AI will help better predict and avoid machine failure, according to McKinsey. This could reduce maintenance costs by up to 10% for commercial and personal vehicles. The one thing we can all hope that doesn't happen is that AI integration into autonomous vehicles does not begin to take over the world like an iRobot, where the AI systems wipe out the black box and information of